Hey there, and welcome. We're going to talk about a kind of fun idea here, and that's the idea that not only can things we've always thought of as being waves, aka light, act as particles, but things that we've always thought of as being particles, say for instance electrons, can actually behave as waves. This idea was first put forth by a guy named Louis de Broglie, a French physicist. It's a fascinating idea because it really challenges your whole notion of matter, and it's actually been shown that if things are small enough, they can exhibit very definite wave-like characteristics. And so there's a couple parts to this. The first part of this is the idea that if something is going to behave like a wave, it has to have certain wave properties. One of those would be a wavelength. So Louis de Broglie showed that the wavelength of a particle actually depends on its momentum. De Broglie wavelength is defined as Planck's constant over the momentum. Let's remember that Planck's constant has the value of 6.26 times 10 to the negative 34 joule seconds. Weird idea, but it turns out this is legit. It works. It also is kind of a fun idea because it explains things like, partially explains things like the quantum states that exist in an atom. If we think of these electrons as standing waves around the atom, that's an interesting idea that would lead to quantized states. Just like as when we were doing wave properties last year, and you learned that you can only have standing waves of particular wavelengths and frequencies, that's the same kind of idea. Being very simplistic about this, but we got to start somewhere, right? So let's just calculate a sample wavelength for something, for instance, like an electron that's moving at a pretty high speed. Let's put it at somewhere like 5 times 10 to the 5 meters per second. Now the mass of an electron is 9.11 times 10 to the negative 31 kilograms. So let's just plug all the numbers in the equation and see what we get. So H, 6.26 times 10 to the negative 34 joule seconds. And the mass is 9.11 times 10 to the negative 31 kilograms. And the speed was 5 times 10 to the 5 meters per second. Putting that in a calculator will yield a result of 1.37 times 10 to the negative 9 meters. Okay, so that's 1.37 nanometers. If that were a photon, that'd be a very high energy photon, but this is an electron. What's important about this is that electrons do exhibit this behavior. If you send electrons through a two-slit experiment like the Young's experiment, you'll actually see diffraction patterns occur. That's pretty good evidence that it's behaving as a wave. Now, we're not going to go much further than this, honestly. We're not going to go very deep into the implications of this. That's really fun stuff, but that's really better left for a higher level college physics course. But it is neat to note, and it is also cool to see that objects can have wavelengths. Now, for something to exhibit certain wave properties like diffraction, the wavelength has to be sufficiently large. So one of the exercises you might do is to calculate, the wavelength of a fastball. And so, just to do a quick estimate, just so you can see that the wavelength would actually be incredibly tiny, let's do what we call an order of magnitude estimation. So we'll just call H 6 times 10 to the negative 34. Let's say a mass of a baseball is a half a kilogram. Now, it's probably less than that, but fine. I'm just, remember, there's an order of magnitude estimation. And let's say that thing is moving 100 miles an hour, which, I don't know, off the top of my head, I'm going to say that's like 3 times 10 to the 1 meters per second. I don't know. I'm just making up numbers here. To estimate this is kind of fun, by the way. Take the parts of the scientific notation that are the numbers. You know, I know there's a formal name for these things. I can't remember what it is. I don't honestly care. In other words, the 6, the 3, and the 0.5. 6 divided by 3 is 2. If you divide that by 0.5, you get about 4. No, not about 4, you get 4. And then if you have 10 to the negative 34 and you divide it by 10 to the 1, you get 10 to the negative 35. Okay, so you're going to see that this is an insanely small wavelength, especially compared to that electron up there. And you're not going to see this ability of a baseball thrown at a high speed to diffract. That'd be really cool, man. But yeah, can't really happen. Too much mass. That's really what it comes down to. It has so much inertia that you're just not going to see this. So anyways, bottom line is that's what you're going to do with the Broglie wavelength, and there's a number of questions on your worksheet, and you can go ahead and have fun with those.